Now that we are done with the prerequisites, we can finally start talking about some actual machine learning. But what does learning in this scenario mean anyway? So in machine learning, there are different learning scenarios. And the first one I want to talk about is what's called supervised learning scenario. And in supervised learning, you have a collection of labeled examples. This is your data set, where each instance of the data set is a tuple containing 2 entries. The first entry is called your feature vector, and the second entry is called your label associated with this observation or this instance. And your feature vectors come from some input space, whereas your output labels come from some label space. So usually, without further notice, we will assume that the input space is R to the D, so there will be exceptions, but not for this module. And we will not further specify the label space for now, because we will do so later when we talk about different kinds of supervised learning scenarios. And the goal in supervised learning is to find a reasonable mapping F from the input vectors to the output labels. And the idea is, if you have such a mapping F, and I give you a new observation that you haven't seen before, it should produce a label that makes sense in the context of the data that you have available. So one example is that you could have the heights and weights of a number of people, as well as their gender as the label. And given this information, you can train a machine learning model that produces this mapping F, which tells you, given an observation of a height and a weight, what the most likely gender for that person is. Of course, the height and the weight of a person is not 100% indicative of a person's gender, but still you can observe that men tend to be taller than women, and a good machine learning model, given enough data, would find this relationship in the data. And given the observation that you have a person who's 2 meters tall and weighs 110 kilos, that will probably be a man. Of course, not always, but the probability of that individual being a man is likely higher than for it to be a woman. Now, the example that I just gave was a classification example. If you assume that there are only 2 genders, then that would be a binary classification problem. So is this individual a male or a female? But if you want to make the assumption that there are more genders than 2, then this would be what's called a multi-class classification problem. In supervised learning, we also have what's called regression problems. And these problems will be the main topic of this module. And there are also what's called structured prediction problems. And these are problems where labels in the label space are of a complicated structure. But I will give proper mathematical definitions to these notions just in a moment. The next kind of learning I want to talk about is the unsupervised learning. And in this scenario, we also have a dataset available, but this time the instances are not labeled. This means that we don't have tuples of feature vectors and labels available, but only the feature vectors. Again, with an observation xn living in some kind of input space. And this time our goal is to find a mapping F that transforms an observation in the input space into another vector or into a value that could be used to solve a practical problem. So I know this definition of unsupervised learning wasn't really specific, but that is because there are so many different tasks that you could do in unsupervised learning. So for example, there's clustering. And in this situation, you have data points. So let me quickly draw a 2D data set. So looking at this data, you would see that there are 2 clusters of data points. And you're not provided a label saying that these instances are fundamentally different to these. But just looking at the structure of the data, the geometric structure of the data, you observe that there seems to be like distinct differences between these 2 data points. And you might want to create these labels yourself then. So maybe this could be customer data And you observe that these define some classes of customers that your company has. Now, this is a clustering problem. Now, let's look at a dimensionality reduction problem. And in that case, you also have data. Let me quickly draw some data points again. Now, looking at the data, we can see that these data points happen to form a line. But we are in 2D space. And it seems unlikely that there will be data points in this area, right? Because all the variance seems to be spread across this axis, this diagonal axis, but not in the axis orthogonal to that. So there's little variance in this direction. So we can transform our data using something that's called PCA and just use one so-called principal component, PC. This will be PC1, the first principal component. And we can project our data onto this principal component. And now we see that after the PCA transformation, so turning these 2D data points into one-dimensional data points, we still retained most of the variance because the variance was spread across this axis, but not the one orthogonal to that. And of course, it might not be a perfect linear relationship. So we squash the points that would be a little above and below the line onto the line. And this is why I chose a slightly different color to the untransformed data, because using PCA or any dimensionality reduction technique leaves your data transformed. And there's a way to undo this PCA transformation so that you get back two-dimensional data points, but they will exhibit a perfect linear relationship. So there will not be the original data points anymore. They will be close to them, but you lost some information by compressing the data onto a lower dimensional plane. And finally, there's outlier detection. And the intuition behind that is really simple. So you have, again, some data. So in this case, the data is generated by a two-dimensional Gaussian density. And this is why we have this elliptic cloud of data that is concentrated around the mean, and the whiteness is determined by the variance of that density, or the covariance matrix in a two-dimensional case. And the question now is, given a new data point, let's say this one, you can hardly see it amongst all the other data points. How likely is this data point generated by your data generating process? And in this situation, you would say, okay, this point looks so similar to all the other points. It probably is generated by my data generating process. But now if you observe a data set that is really far away from the rest, let's say this one, for example, then the probability of that data point being generated by the data generating process that you assume to be true is so low that you would consider this to be an outlier. One example where outlier detection might be useful is in a fraud detection, where you have customer behavior. So these two axes describe some kind of customer behavior, and you have a collection of non-fraudulent customers. Now observing really unusual customer behavior might be indicative of that individual committing some kind of fraud. So you might want to have a look at that. So these are examples of clustering, dimensionality reduction, and outlier detection. Now the next learning scenario I want to cover is semi-supervised learning, in which you have a collection of both labeled and unlabeled examples. And the situation is similar to the supervised learning problem, where you want to find a mapping F that maps from the input to the output space. And although we don't have labels for all the instances, we could still exploit some structure in the unlabeled instances to aid our supervised learning algorithm to find a useful mapping F from the input to the output space. Now, this learning scenario is what people usually think about when talking about machine learning. And this is reinforcement learning. And in reinforcement learning, a machine lives in an environment, and this machine is capable of perceiving the state of that environment as a feature vector xs. And The machine, similar to a game, can execute actions in every state that it perceives, and every action brings different rewards. And the machine learns a policy or strategy F, and the policy has as input the state, and it should output the optimal action for that state. So one example of the scenario is your machine living on a checkerboard, and the machine is supposed to reach this field where there's a reward, and on the way to the reward there are fields that give some kind of penalty to the machine. So X's give like 5 points of penalty, minus 5 points, and green fields award 100 points. And every step costs 1 point. So if the machine had access to the entire board, as well as the positions of the reward and the penalties, then it could find the optimal route. And I assume the optimal route is that way, because going that way might be a little shorter in amount of steps, but you have to pay these additional minus 5 points to enter this field. But the problem is made harder by the machine only being able to perceive the fields adjacent to the field that it's standing on. And this would be an example of a reinforcement learning scenario. So in the beginning of the section, I briefly touched on supervised learning. But let's go deeper and study the different manifestations of supervised learning, and let's start with classification. Now, recall that in supervised learning, we always try to find a mapping F that maps from some input space to a label space. So this is our Y. This is our Y. And since in this definition we haven't specified the concrete structure of the input space, the input could be anything. It could be tabular data, images, text, audio, anything. And the output labels, Y, they live in an index set. And these indices refer to class indices. So you could have indices for fraud, no fraud, and this would be an example of a binary classification problem. You could have a sentiment analysis problem where you have multiple classes that you want to predict. So the sentiment of a text could be negative, it could be neutral, or it could be positive. So let me draw a picture again, because I think that helps with the understanding of the topic. So in this scenario, we have two input features, x1 and x2. And if we plot our data points in this Euclidean space that is spanned by these two features, then we might observe that if we color code these data points corresponding to the associated labels, that we have certain clusters that form. And we might want to find what's called a hyperplane that separates these clusters. And we may call this hyperplane a decision boundary. Decision boundary. And roughly speaking, every data point that lies to the right of this decision boundary will be classified as class 1, whereas every data point to the left of the decision boundary will be classified as belonging to class 0. And if we observe a new data point for which we don't know the label, then our decision boundary will then tell us how to classify this data point. Now in this case, our classification model will assign the class label 1 to that novel data point. Now this is an example of binary classification. We may also have the situation where we have more than two classes. And such a situation where we have more than two classes, we call a multi-class classification. Another kind of supervised learning problem is the regression problem. And again, this will be the focus of this module. And here again, we have unspecified inputs. So it could be tabular data, it could be images, it could be audio signals, and we produce a real number as output. And examples of regression estimation problems would be the estimation of a price, for example, of a stock. Could be the estimation of temperature at a given date and time at a specific location, or it could be the weight of an object given some of its properties, and so on. And finally, in structured prediction, we have a label space Y, where the elements in that label space are of complex structure. So one example of a structured prediction would be image segmentation. And let me quickly draw images for that. So this is the goal of image segmentation, where you have an input image of, let's say, a autonomous vehicle that is equipped with cameras, and it captures the street scenery, and the structured prediction algorithm inside the car should produce for each captured image. So this is a video stream that the car records. For each of the individual frames, it should annotate structure in this street scenery. So you have a classification for each pixel, and the car will essentially see that, okay, this red structure is a traffic light, and this orange structure is the road. The green pixels correspond to the sideway, and all the other pixels correspond to miscellaneous classes. So of course it would also be useful to classify pedestrians and other cars and vehicles on the road, but you get the idea. So this was an example of image segmentation. Or you could also have a structured prediction problem where your mapping F creates text. So for example, if you give it some suggestions, some keywords, it inspires the mapping to write a text, a short story, or a poem. Or it could create code segments. So if you've heard about the GitHub Copilot, then this is an exciting model that produces code for you. So this is also a structured prediction problem. But your model could also produce path trees or molecule structures or anything else that you train it for. Now observe that we are still in the supervised learning scenario. And in supervised learning, we will often make use of so-called loss functions. And here is a formal mathematical description of what a loss function is. So let X be the input space and Y the output space. And a loss function is any function L that takes as input a triplet. And the first entry is an element of the input space. The second entry is an element of the output space. And also the third entry of the loss function is an element of the output space. And this function, taking this triplet, always produces a positive number. We call such a function a loss function. Any function that satisfies this property is a loss function. Reasonable candidates that we'll be using all the time, essentially, are the absolute deviation. So we will denote it with this L1. And the first input is the observation itself. Then we have the prediction of our model as the second argument. Then we have the true label Y as the final argument of this loss function. And L1, the absolute deviation, is just defined as the absolute difference between these two. And we take the absolute value of this deviation, because if we don't, then we might have positive and negative deviations. And if we then add all these deviations over a test data set, for example, then these deviations might cancel out. And this would give us the impression that we did fewer errors or errors of smaller magnitude than we actually did. And then you might ask yourself, okay, so in this definition, the only values that we consider is the prediction and the true label, right? So why do we have the x as an input argument? The reason for that is there might be cases in which a false prediction might be more costly than in others. And the input vector could give us an indication for such cases. So for example, if we were to produce a prediction for a disease of a given patient X, then our prediction of whether that person has this kind of disease is f of x. The fact whether this person has this disease is labeled y, but the information about the patient is stored in the feature vector x. And it could be that some people should be classified with more care, because it might be that elderly people are then more affected by wrong classifications than younger people, for example. And you want to account for this imbalance by at least allowing the input argument to be considered by your loss function. So in this case, it doesn't really matter. All the misclassifications have the same weight if you average over the dataset, but you might want to include different weightings according to the input vectors. And a second natural candidate for a loss function is the squared deviation. And this is because the square will turn this deviation positive no matter what. But also squaring will amplify larger deviations, so it will penalize larger deviations more heavily in our optimization problem, and smaller deviations will be more neglectable. And now, since we have this notion of a loss function, we can define what's called the true risk. So let's go through this definition. So we have a mapping f from the input space to the output space. We call this a prediction model. And we have a loss function as defined on the previous slide. Now the true risk RL of a prediction model with respect to L is defined as follows. So the true risk RL of a prediction model F, that's the argument, is defined as the expectation of the loss of that prediction model. So just for the sake of completion, this expectation is a double sum over all input-output combinations, x and y, of their joint density times the loss that occurs when a certain combination is present. And we take the integral over all x's and all y's. So this is a mouthful. This is a lot, but what it basically is just the weighted average. This is the weight, the probability of two values occurring together of the loss that is associated with that combination, given the model that you specify. Now, the expectation is over tuples x, y, drawn from the data generating process pxy. This is what I specified with this weighting of the loss. And this phrase is in bold letters because I thought it was important. The goal of machine learning is to find a prediction model Fn, and n stands for the number of data points we have available, with the lowest true risk possible. So we turn this expression into a quantity we want to minimize. We want to decrease the expected loss over all possible input-output combinations. So as you can probably imagine, finding a prediction model that minimizes the true risk is a really difficult problem. So let's be really strategic with how we approach this. So for this purpose, let's introduce some additional definitions. So let calligraphic F be the set of all possible prediction models. And this means that we collect all functions that map from the input to the output space. And we restrict the space by only considering those mappings F that are measurable. This is so that we can calculate probabilities later. Also, let RL be the true risk of F with respect to some loss, as defined before. Then we call R star L, which is the infimum of all true risks that we get by considering all these functions f in calligraphic f, the Bayes risk. This is the Bayes risk for our problem setting. So let's have a closer look at this so that we are all on the same page. In case you didn't know, the infimum is the largest lower bound of a set. Now let me be a little informal, so mathematicians cover your ears. But you can think of the infimum as the minimal, the smallest element within a set. So the Bayes risk, this quantity is the minimal true risk that we could achieve by considering functions f that live in calligraphic f, so that are measurable mappings from input to output spaces, right? So this is actually the solution to the optimization problem I formulated on the previous slide. This is the true risk that we want to achieve. And the Bayes predictor, another term that we introduce, is the prediction model f yielding the Bayes risk. So a prediction model f star that minimizes the true risk, right? So this is what happens here. We call the Bayes predictor. And this is the model that we want to find. But how do we go about finding such models? So we use what's called a learning algorithm, and I will denote learning algorithms with this A. And these algorithms look at the data essentially and produce some kind of mapping as output, and this will be the mapping that you're left with. And ideally, we want this algorithm to be consistent, and this means that given enough data, your learning algorithm will produce the Bayes predictor. But let's define this formally. So imagine we have an infinite sequence of data points. And this means we have this infinite sequence of input-output combinations, which are all drawn IID from the data generating process PXY. And by Fn, we denote the prediction model that was selected by an algorithm A after the first n observations. So after the first capital N observations of these input-output combinations, the algorithm A selects the model Fn from the space of possible prediction models. We call A consistent with respect to P, the data generating process, if and only if the risk RL of the model that was selected by the algorithm converges in probability to the Bayes risk. And just as a reminder of what convergence in probability means is that for every epsilon greater than 0, we have that the limit as n goes to infinity of this probability goes to 0. So this event is that the deviation between the risk of the model that the algorithm is selected after n observations and the Bayes risk, which is the lower bound of risks that are possible, exceeds epsilon. The probability of this event occurring should go to 0 as our number of observations grows to infinity. We call A universally consistent if and only if it is consistent for all possible data generating processes, right? This definition, this above part, specifies that for a particular data generating process, this algorithm A is consistent. But being universally consistent is much more of a requirement because it says no matter what the data generating process is, the algorithm A will eventually find the Bayes prediction model. Let that sink in. It's nice to see that Some algorithms we use in practice are proven to be universally consistent even. So one example is the support vector machines, but also random forests and AdaBoost and many, many more were proven to be universally consistent. So if you're interested in studying how to construct proofs for universal consistency of a learning algorithm, then you can check out these references, which are also at the end of the presentation. So in general, we don't know the data generating process, PXY. This is the entire game of machine learning, that you don't know the joint density of your inputs and your outputs. Otherwise, you'd be done. And as a result of not knowing the precise structure of our data generating process, we cannot compute the true risk. So we've been talking about the true risk all the time now, but we can't even compute it. But what we have is a finite sample of inputs and outputs. So we can approximate the true risk with the so-called empirical risk. And this is based on the sample. So it's a weighted average of the empirical loss that we observe, right? Because we have the inputs available. In training situations, we have the labels also available, the outputs. And of course, we have our predictions. And then we can calculate the loss for each observation, add them up, and divide by the number of observations that we have. Now to the first proof of this module. So the statement I want to prove now is that the empirical risk, as defined on the previous slide, is an unbiased estimator of the true risk. And this is a useful property because this tells us that using this definition, we will produce an estimate of the true risk that is not biased in a sense. So let's do this really formally. So recall from your statistics classes that we can produce an estimate of a parameter living in some parameter space based on a sample. And the estimator is the function t that produces this estimate given some sample as input argument. So this is just the difference between an estimate and the estimator. And again, we want to prove that the empirical risk is an unbiased estimator of the true risk. So we've now clarified the estimator part, but what does unbiased mean? So an unbiased estimator is an estimator that produces an unbiased estimate of the parameter that you want to estimate. So the bias of an estimate set ahead is defined as the expectation of that estimate minus the parameter you're trying to estimate. And we have the expectation of that estimate because the estimate is a random variable, because it depends on the input argument of t, and the input argument is a dataset which is drawn from the data generating process, and therefore the dataset is a random variable. And a function of a random variable usually tends to be a random variable itself. So, given this definition of the bias of an estimate, we have that the estimate is unbiased if the expectation of that estimate is equal to the parameter we want to estimate. Okay, now let's check whether the empirical risk satisfies this for the true risk. So we have the expectation of the empirical risk. And this is defined as such. And then we recall that the expectation is a linear operator. So linearity of the expectation. And this gives us the possibility to push out the factor 1 over n as well as the sigma. So we get the weighted sum of expectations of empirical losses. And since this is the same term for every n, we sum up n of these expectations of true losses, and we end up with 1 over n times the expectation of the empirical losses, and we see that these cancel, and that this corresponds to our definition of the true risk, and this concludes our proof. We have shown that the expectation of our empirical risk is equal to the true risk. And this is our definition of our estimate being unbiased. And since the estimate is unbiased, the estimator, the empirical risk, is an unbiased estimator of the true risk. Now that we've seen that the empirical risk is an unbiased estimator of the true risk, it makes sense to minimize the empirical risk as a proxy for the true risk, which we cannot assess since we don't have the access to the data generating process. Unsurprisingly, we call the approach of minimizing the empirical risk minimization. So in this procedure, we have as given a dataset, a finite dataset containing n elements, where each element is a tuple containing an input observation, as well as a label associated with that observation. And then we select a loss L, and we use it as a performance metric for the prediction problem. And based on how much computing resources and time we have, we select a set of learning algorithms, and each one of these is indexed with a j. And we run these learning algorithms on our finite dataset. And this set of algorithms induces a set of possible prediction models, and we will denote it with this calligraphic H, which is a subset of all possible prediction models. And from the set of possible prediction models that is induced by the learning algorithms we run on our dataset, we choose that one prediction model that has the smallest empirical risk. So within that set H, we have a lot of prediction models that could be found by our learning algorithms, and we choose that one that has the smallest empirical risk based on the n data points we have available. Now, since the empirical risk is an approximation of the true risk, and we're interested in minimizing the true risk, again, that's the goal in machine learning, we can define an object of interest, which is the best true prediction model in H. And this is that particular prediction model that minimizes the true risk instead of the empirical risk, as on the previous slide in the empirical risk minimization procedure. Now, using the empirical risk minimization procedure, we will produce two kinds of errors. The first kind of error is the estimation error, and that's the true risk associated with the prediction model that was identified by our empirical risk minimization procedure, and the true risk associated with the best function in H. And since the true risk associated with f tilde is always smaller or equal than the true risk associated with the model that was found by our learning algorithms, we have that the estimation error is always positive. And then we have the approximation error, and that's the difference between the true risk associated with the model f tilde, the best one in H, and the Bayes predictor, which may lie outside of H, but is within the set F, the set of possible prediction models. And since the set H, which is induced by our learning algorithms, is a subset of all possible prediction models, we have that the true risk associated with the Bayes predictor is smaller or equal than the true risk associated with the best prediction model within H. And this also leads to the approximation error being always positive. So at this point, I think it makes sense to visualize this. So we have the set of all possible prediction models F. And within that set, there's the set of prediction models that our algorithms can possibly find. And within these two spaces, there are 3 different functions of interest. So this first one is Fn, and this is the model that our algorithm finds. And then we have F tilde, which is the best possible model in the class of functions that we consider by using our set of algorithms. And finally, there's F star, which is the Bayes predictor, the best model overall, the best possible model. Now the distance between the function Fn, which was the function identified by our empirical risk minimization procedure, and the function F tilde, which is the best model in age, the best model that could be found by running our learning algorithms. This is the estimation error. Whereas this distance, the distance between F tilde, which is the best model in age, and F star, which is the Bayes predictor, the best model in F of all possible function, this distance is the approximation error. Now, in the context of machine learning, you may have heard of these two terms, under and overfitting. And they both relate to the expressiveness, the size, the power of age, which is induced by the learning algorithms we run. And age, we also sometimes call the hypothesis class. And this is because by selecting a set of algorithms, we make assumptions about the data. So depending on the size of age, the expressiveness of the model space that we search in, we may end up with underfitting or overfitting, both of which are not desirable. So let's first start with underfitting. Underfitting happens if our hypothesis class is too small. And the result is that we have small estimation error, but large approximation error. Now, if we go back and look at this illustration again, we see that if age was really small, then there's a good chance that the model that we select by doing empirical risk minimization is very close to the best possible model within that class, right? So the estimation error will be small. However, if age is really small, then it might be that this entire hypothesis class is far away from the best possible model, F star, and therefore the approximation error will be quite large. The opposite problem is overfitting, and this is if your hypothesis class age is too large, you have too many functions to choose from. And the result is opposite to underfitting. This time you have large estimation error, but small approximation error. So let's have a look at this illustration again. So let's imagine age approaches F in size. Then the distance between F tilde, the best model in age, and F star, the best model in F, will be relatively small. So we have low approximation error. But since we are now considering so many more functions, it's really hard to find the best one. Therefore, the model that is selected by our empirical risk minimization procedure will likely be far away from the best model in age, and therefore the estimation error will be larger. Now I drew some more pictures to illustrate the concept of under and overfitting data. And we have the same data set 3 times. Now let's consider the hypothesis class of linear models. Then no matter how sophisticated our approach to finding the best function within that space, we will always end up with a poor performing model that might look like this. So it doesn't even fit the data points we have available. This is what's called underfitting. So if we, on the other hand, have a hypothesis class consisting of all polynomials up to degree 100. And we have so many functions to choose from that our empirical risk minimization problem is essentially solved. We can choose a polynomial that might look like this. So we see that this high order polynomial function might capture the relationship between the observed data points, But what is bad about this overfit model is that it doesn't generalize to new observations. So if we look closely, we see that the true data generating process is something like a quadratic function. And if we were to now observe a data point x that lives down here, then our model would suggest this value of y. Whereas in reality, it's more like this if it's truly a quadratic. So even though an overfitting model fits well to data points you have observed, it fits only poorly to new data points. So we call this overfit. Now, recognizing that the true data generating relationship between x and y is a quadratic one with some noise, you would like to fit this quadratic function as your model. This would be the ideal fit. So now we've discussed the estimation and the approximation error associated with doing empirical risk minimization. But another interesting and important error decomposition in classical machine learning literature is the bias-variance trade-off in L2 regression. And this means that we're interested in decomposing the expected quadratic error, which is the expectation of quadratic deviations between the predictions we generate with the model that was selected by our empirical risk minimization procedure and the predictions that are generated by considering the perfect model, the Bayes predictor. So by expanding this expression and doing a lot of rearranging, you arrive at the conclusion that this expected quadratic error decomposes into a variance term only involving the prediction model that was selected by our empirical risk minimization, and a bias term, which is the squared difference between the expected prediction that we generate by running our learning algorithms and the ideal prediction. And this variance term, if you look at it sharply, you will see that this is the definition of the variance of a random variable. And in this case, the random variable is the prediction model that is selected by our empirical risk minimization problem. Thinking about it, you will realize that indeed this model Fn is a random variable because the model that we select by performing empirical risk minimization is based on the sample that we have available. And the sample is drawn from the data generating process and is therefore a random variable. And since Fn is a function of that data set, it is also a random variable. So this expression makes sense. And this bias term on the right is a measure of how much the expected prediction that we find and the ideal prediction that we could have deviate. Now this is a really nice illustration that gives you some intuition behind the bias and the variance terms. So ideally, when aiming for this target, we would like to hit the bullseye at all times. And in that case, we have low bias, low variance. So it might be that our aim is good, but the rifle we're using is poorly calibrated so that the bullets scatter around our average shot, which is the bullseye. And in that case, we have low bias because our aim is ideal. We target the bullseye, but we have high variance because the shots just scatter around it. And only on average, we hit the bullseye. And then it might be that we have a good rifle where the scattering is minimal, but we don't aim properly for the target, right? And in that case, we have high bias because we're not aiming for the bullseye. But we have low variance because the shots that we take, they don't scatter around all that much. And then the worst case where we have high bias and high variance, where the shots are just all over the place. But we are talking about the bias-variance trade-off. So it seems like we can't have both, low variance and low bias. And a historical paper from Geman and colleagues is called The Price to Pay for Achieving Low Bias is High Variance. And this paper actually coined the term bias-variance trade-off. This paper is often cited when we talk about the bias-variance trade-off. So what is the bias-variance trade-off in machine learning? And the basic idea is that as the capacity of H increases, so does the variance in our bias-variance decomposition. So this is the variance. But in underfitting, we've seen that if we go for a lower capacity of age, then we end up with a model class where no models in it do the data generating process truly justice. And therefore, as the capacity decreases, we have increasing bias. And actually, the term in the bias variance decomposition is a bias squared term. And since the total error is the sum of these two errors, we have that the total error has this U shape. So we see that the minimum of the total error is somewhere in the middle, right? So as you increase the capacity beyond that point, you have higher variance leading to a higher total error. Whereas if you decrease the capacity of your hypothesis class, you increase the bias and therefore the total error. So we see that increasing the capacity of age beyond the point of minimizing the total error, that this leads to more overfit. And if we decrease the capacity of age below the point that would be required by finding the minimum of the total error, we have that underfit increases. Now I want to convince you that this decomposition is actually true, so that if we talk about an expected quadratic error, that this decomposes in a variance and a bias squared term. So for this proof, let's introduce the following notation. The ideal prediction we will call theta, and the prediction made by the prediction model that we found by running our algorithms in the context of empirical risk minimization. This is a random variable and our estimate of this quantity. I will now show that for general estimation situations where you want to estimate a fixed quantity theta by an estimate theta hat, that the expected quadratic error will decompose always into a variance and a bias term. So let's write down the definition of the quadratic error. And what I do now is that I add and subtract this fixed quantity, the expected value of our estimation. So you may be wondering why I insert these quantities. And that is because we can now treat this first bit as A and the second bit as B and employ one of the binomial formulas. So we have this decomposition. And using this binomial formula, we arrive at this large expression. But we can tidy this up by employing the linearity of expectation, and we are left with these three terms then. Now we have to realize that the expectation of a random variable is constant, and therefore this expression is also a constant, the squared deviation between the expected value of our estimate and the quantity to estimate. This is a constant. And if we look at this expectation, we see that this expression shows up in the expectation, right? So we have the expectation of a constant, and this means that we can just drop this expectation because the expectation of a constant will be the constant, right? So this entire thing will be just the argument of this expectation. Also, we observe that since the expectation of our estimate is a constant and theta is a constant, that this part will also be a constant. And then we can employ linearity of expectation again to turn this term into that one. And that way we are left with 2 times this constant times the expectation of that thing, that bracket. And then again, linearity of expectation allows you to push this expectation inside the bracket, and you will see that you subtract the expectation of the estimation from the expectation of the estimation, and this will be 0. So this entire thing will be 0 and vanish, and we are left with only this and this term. They reoccur here. And we observed that this is just the variance of our estimate, and this is the bias squared of our estimate. And therefore, we have shown that the expected quadratic error decomposes into a variance and a bias squared term, concluding our proof. So I hope this was all really convincing, but there's a caveat. So empirically, what you can see is that although this decomposition is definitely true, that the quadratic error decomposes into a variance and a bias term, it is not clear why the variance term should increase as the bias decreases and vice versa. So there's a somewhat current study conducted by Balkan and colleagues that investigates the capacity of neural networks. We will cover neural networks in a later module of this program. But what you might know about them is that they have millions and billions of parameters, many more often than available data points. And this basically shouts overfitting. You have so many parameters, how could you not overfit to your data? So this is the classical depiction of the bias-variance trade-off, as I've explained on a previous slide. On the x-axis, you have the capacity of H, and on the y-axis, you have the risk. And we called that the error on a previous slide. And let's first look at this training risk. This is the risk associated with the data points that you have available, your training data set. As the capacity of H increases, the training risk approaches zero. And that is because the more complicated the space of functions that you can search, the better the fit for the data points you have available. We've seen that that's overfitting. The test risk, on the other hand, exhibits this characteristic U-shape. So the minimum risk is actually for a moderate capacity of H. And anything below that will lead to underfitting, whereas anything above that will lead to overfitting, worse generalization to new unobserved data points. Now, what Balkan and colleagues propose or found empirically was that this classical depiction is true up to the what they call the interpolation threshold. And that is where the model starts being over-parameterized. It has more parameters than available data points. So it seems like that if you increase the capacity of H up to the interpolation threshold, your test risk will increase. Your model will exhibit overfitting behavior. But after this interpolation threshold, as your model becomes more over-parameterized, the test risk will actually decrease. So what you actually want to have is a model that performs perfectly in your training data. The predictors to the right of the interpolation threshold have zero training risk. And you see that as you increase the number of parameters in your neural network, it seems like the test risk, the generalization error, will decrease. Crazy, right? But if you want to learn more about this, then you can check out this excellent blog article of Brady Neal or his publications on this issue for greater detail. So if you don't want to study these additional resources, let me quickly summarize what Mr. Neal suggests. And that is that we update our textbooks, our mental models, and courses on machine learning. And this is what I'm doing right now. I'm updating the standard curriculum of machine learning in this course. And the first update is that we should not consider the bias-variance trade-off as being universal. So you can see empirically for a large number of parameters in neural network architectures that this just does not seem to be true. So let's be critical of this classical notion of bias-variance trade-off and consider modern empirical results on this matter. The second update is actually what confused me in the beginning when I first learned about the bias-variance trade-off, because obviously now, having seen the proof, you should be convinced that the decomposition itself is true. But it does not imply a trade-off. Why should the variance increase as the bias decreases, and vice versa? And finally, loose bounds should not be interpreted as necessarily predictive of the quantities they bound. And this is what Neil Shing's contributes to this misunderstood concept of the bias-variance trade-off. But excellent, we finished this first section of actual content. And next time, we'll delve into linear regression.